Right, well, good morning. Welcome to MeetBSD. My name is Robert Watson. I am a member of the FreeBSD core team and on the board of the FreeBSD Foundation. What I will be talking to you about today is network stack optimizations on FreeBSD. These are changes that have arrived between about FreeBSD 4 and the forthcoming FreeBSD 8. So I thought I might take a quick little hand. If you were a hardcore network stack kernel hacker in the audience, could you raise your hand? Right, this talk is actually not for you. Okay, if you're a kernel hacker and you're in the audience, could you raise your hand? Okay, I got some source code, so you'll be happy. Most of this talk is for everyone else in the audience. And so this isn't really a kernel hacking talk. I'm not going to show you a lot of source code. But I will talk a little bit about the design, the approaches, some of the techniques we're using. And I'll start out by talking about trends in hardware and operating systems, because operating system development is basically driven by changes in hardware. As networks become available, we start doing all this networking stuff. As the CPUs get faster, the optimizations techniques change. Memory gets really big, and you discover all your tuning parameters are wrong. CPUs grow caches, and suddenly the nature of performance enhancement really changes. You're looking for completely different things. So I'll talk about that a little bit. Then I'll introduce the TCP input and output paths. I'll show you pictures that some of you will think are sideways, but that's all right. I'm even going to be right on the left. It's fine. I'll talk about some specific optimization techniques that we both take advantage of in hardware and purely software approaches to improving performance. And as I said, this is not really for network stack hackers, but you might find it useful anyway. I'll talk a little bit about the goals in performance optimization. There are basically two goals. You want to make more efficient use of the hardware that you have. You want to make it more available to the application programmer. And you want to improve the effective bandwidth or performance of the stack, how much bandwidth is available to the application to use. And this can mean lots and lots of different things, depending on the context. But I thought I'd show you kind of two quick pictures to sort of wave my hands in the performance direction. Although this is a talk about performance, I'm not really going to show you very many measurements. What I'm going to do is talk to you about why we make the changes that we do and how they integrate with the stack. So how does this work out? I have two pictures here. One of these on the left is a picture of CPU usage as you scale up the number of processes in a system performing TCP at the same time. And in particular, I split each vertical bar into two parts. The green part is idle time, the red part is time spent in interrupt, and the blue part is time spent in system. In none of these graphs does the user process appear anywhere. That's because the user process in these graphs is basically just sending data, which is really easy to do. There's not a whole lot of work in sending data. So interestingly, the network stack is doing almost all of the work in the operating system. So it makes a big difference if we can start reducing some of these numbers. We can start reducing the amount of system time or interrupt time. We really will make more CPU time available to the application. So another lesson from this graph, and this graph is from before most of the optimizations we made, is that you can really burn a lot of CPU time doing it, and especially as you increase the level of concurrency. So as you move from the left to the right of the graph there, we're starting out with one process and one core generating network traffic. And then as we move to the right, we have more and more processes. And each one of these is a pair of them. One is with TCP segmentation offload, and one is without it. And what we basically see is that as we add TSO to the graph, we get a minute increase in the available amount of CPU cycles. On the other hand, we actually see that if we go to two processes, we get a significant improvement in network performance. And then actually at some point it goes down. So this is before a lot of the changes that we made. But I think it's instructive because it shows you that one of the things that happens as you increase the amount of parallelism is that you may burn a lot more CPU time doing work, but you may actually not realize benefits in terms of network performance. You're wasting a lot of CPU capacity doing things that you actually don't need to do. And so an obvious thing to do when you want to improve performance is to try and cut down on these numbers, which is what this is about. Also on the right-hand side, you notice in this picture we're capping out about, I don't have a scale, but that's 9 gigabits out of the available 10 gigabits. I think this hardware should be able to do about 10 gigabits, so clearly there is room for improvement. But it's interesting that on one core we're actually getting well over 6 gigabits a second, even before a lot of the SMP enhancements for the last couple of years. So what are the changes in hardware that drive the performance changes? Well, the first one is it's been going on for about 15 years, I guess, or 20 years, and this is a gradual change in the optimization goals in performance work, and that's that CPUs can grow in caches, memory is far away, memory is slow, so we use caches to improve performance. This means that it's suddenly okay to burn instructions if you can reduce cache misses. So the optimization approach, up until the 1980s, on this hardware was we want to reduce the number of instructions. And as you get beyond that point, you get to modern CPUs, what you really want to do is increase the instructions so that you can spend fewer instructions locked in a cache miss. You don't always want to increase instructions, but if you can, it's a bit more like the decisions you make when you're doing disk layout. When you implement a file system, you're willing to burn a lot of CPU cycles in order to get decisions right, because the cost of getting them wrong is really significant, tens of milliseconds. It's not quite that bad with CPUs, but you begin to see a design philosophy that really optimizes in a different way. This actually causes us some trouble, because lower-end embedded platforms are still instruction-centric in optimization. So if you begin to optimize your network stack for high-end hardware where cache performance is really the issue you're worried about the footprint, you're worried about cache misses, you're worried about trying to structure things so things don't depend on data that you only get as a result of a cache miss, you may actually hurt performance in embedded platforms. So there's a tricky trade-off. We see caches moving down and getting into lower and lower end pieces, and so that optimization approach becomes more applicable in embedded environments, but there's still a tension there. Another hardware direction that has really changed the approach is that we're seeing a dramatic decrease in the improvement of the performance of individual CPU cores. Most of you have noticed it's really hard to buy a decent notebook without multiple cores now. So we have parallelism even in notebook computing hardware. It appears in the embedded space. So suddenly we're very, very interested in multiprocessing. Well, not suddenly. We've been interested in it for about 10 years, but suddenly we're making progress. So this is useful. Another trend that I think is useful to look at is the fact that the network has suddenly gotten a lot faster than CPUs again. So there's this sort of cycle in which available network technologies for server farms and end-user systems gets faster and slower over time with respect to CPU. And right now the network significantly outpaces individual CPU cores. And in fact, when you're working at 10 gigabits, most notebook computers won't be able to keep up with that in practice. So we're interested in using these multiple cores to try and use the network more effectively. So what does this mean? We want to use multiple cores, but we also want to offload services into the hardware. So a section of this talk will be about what kind of things should be offloaded to hardware and what is the impact for the operating system. So what do? We want to change the operating system. That's sort of the starting point for an operating system talk. We want to manage the cache footprint in ways that are better. We want to use measurement tools to understand how we're using the cache. We want to understand what the dominant cache misses. One of the most important things when you're doing networking processing is to not take the cache misses in the wrong place. A packet arrives on the system, you have to look at the data in the packet, so you have to take a cache miss on it. But do you take the cache miss on the right CPU or the wrong CPU? Does that mean you actually miss twice as the data migrates effectively between CPUs? We're interested in rebalancing instruction versus cache optimization approach, as I mentioned. We're interested in more parallel processing. We're interested in offloaded network protocols. There's a bit of background. Again, let's talk about TCP. TCP is the transmission control protocol. It is a stream protocol. This implies a lot of things, but some of them are particularly interesting. TCP is reliable. You want all the data to get there. But very importantly, you want the data to all arrive in the right order. And this is a guarantee that the sockets interface that TCP provides, and TCP works very hard to provide on the wire. And it turns out that one of the implications of the design of TCP is that if you start misordering packets on the wire, TCP becomes slow. It behaves badly. It recognizes certain behaviors. It sees packets arrive in the wrong order. It assumes that a packet is missed. It decides it's going to retransmit some packets automatically. This is improving, but I think it's fairly fundamental to the way we build networks. So we try to keep packets in order if they're part of the same flow. And as you begin to add parallelism to the operating system, it becomes very important to maintain that ordering also. There's the opportunity to misorder things if you run them on different CPUs at the same time. So I have here sort of a sketch of two network stacks, and we'll take a close look at those in a moment. This is the TCP input path. People draw this picture in many different ways. Usually you kind of have the hardware at the bottom, and as you move up, you reach the application at the top, but sometimes people do it the other way around. I've done it sideways, so they more correct. When packets arrive in the network stack, in the hardware, they basically turn up in this physical device that we call a network interface driver. Now these things, network interface, these things are very sort of amorphous. They look different from each other. But fundamentally what they tend to do is actually look at the very lowest level parts of the packet and then just pass a pile of data up the network stack. We then have a device driver, which will start to interpret what we call a link layer. This is the bottom of the Ethernet frame. What's the MAC address? What protocol type it is? Where does it go next? We pass it up to IP most of the time, where it will do some checksum validation. We want to make sure the IP header is correct. Then we pass it up to TCP layer. One of the things we do here is that we start recombining these packets. So when we transmit, we break them up into these little pieces with a packet-oriented network. So we begin to sort of slap them back together again. But we have to look up a socket right now to do this. So we have to go and find out where the packet's going to go so we know what to reassemble them with. Then we stick them all together in these multiple packets. we'll pass it up to a socket, and eventually it ends up in user space in the application where it's sort of perceived as a byte stream. Julian.
I think you've got an important part missing there, which is that more and more there's another blob hanging off the edge of the IP, which is the firewall, where you're doing all sorts of random inspections of the code and of the packets
right,
and so on.
This is a very layering-oriented thing, so firewalls are not very layering-oriented. They're just a fairly strange.
Well, I'm just saying,
strange things on a stack too.
It can make a very big difference to what you're doing for performance-wise. That's all.
Right, and actually, I'll talk a little bit later about when I talk about TCP offload. I'll talk about the fact that the firewall doesn't fit well into this picture and causes some interesting things to happen. But this is kind of a high-level picture. Along the bottom, what I have is a picture of the threads in the kernel that are involved in processing it. So threads on modern operating systems represent sort of streams of sequential computation. They tend to represent particular tasks or particular activities. In our kernel, we have an iThread for each device. Sometimes we have multiple iThreads per device. This processes the lowest level parts of the device driver when an event comes in. We then walk up, historically we walk up to something called the NetISR, which essentially is a software iThread. This is a separate computation context where we look at packets and we deliver pretty much the socket. And then finally the user thread executing a kernel will come and pull the data out of the socket and then copy it to user space. And one of the things that we'll see is that if we start moving all these lines around, the performance properties change a lot. Let's talk briefly about the TCP output part. The application has a stream of bytes. It's going to pass it down. One of the first things we do is we break it up into these chunks. There's sort of these things called clusters. We pass it down to TCP. TCP starts breaking them up into packet-sized chunks. We don't actually do that at the top level, interestingly. We start wrapping them up in headers and calculating checksums. We pass them down to IP. We do more headers and more checksums. We pass it down to the link layer, where we do even more headers, but not the checksum. We then pass it off to the device driver, which will do the transmit. I was kind of looking to see if I could find any situations in which we generate the link layer header, link layer checksum in software, really, except for encapsulation special devices and local synthetic devices. It's always done in hardware, and this turns out to be beneficial. So let's talk a little bit about offload. So in that picture, we have all these lines. Almost all the lines are in software. The hardware device is this tiny little thing over on the side. Well, it turns out that hardware device vendors like to make their devices look faster and sell better in the market. And one of the ways that they can do this is by pulling software parts into hardware. They can do it more efficiently, or possibly they can just do it in parallel. They may not be able to do it faster, but at least if it occurs concurrently, that frees up CPU time on the host operating system and the host computing environment. So what do we get when we offload to hardware? Obviously, we reduce the instruction count. We're not doing the checksum calculation. Maybe we're not breaking up and reassembling packets as much. And that's good. But we also reduce cache misses. So in the input picture, we saw that there were 3 threads that were involved. And one of the problems you run into is that sometimes you do these calculations in specific threads where the data doesn't actually normally get handled. Most of the data will be handled by the user application in a completely different thread. So every time you touch the data in one of these threads, potentially on a different CPU, you do a cache miss and it has to get pulled into the cache. And sometimes these things share caches and it works out efficiently. Sometimes they're on the same CPU. But in worst case scenario, you could cache miss on these headers multiple times as you're going through. So if we start to offload functionality that might, for example, touch every byte in the packet to a different to hardware which has to look at every byte anyway, we potentially benefit from a cache perspective. So what kind of things can we offload? Well, checksums are very popular offload because they touch every byte in a packet because they need to in order to calculate the checksum. And that's expensive. There's more recent cards that have, I guess, starting with the later 100 megabit cards, but almost all gigabit cards that are available today, offload portions of TCP into the hardware. And as you move up the spectrum, more and more TCP ends up in the hardware. The hardest core version of this is Co, which is you literally implement the entire TCP stack in hardware, and software just kind of says, oh, okay, I'll just put that in the socket, that's fine. And I'll talk a little bit more about that. There are some other things you can offload too. People offload iSCSI, they do a bunch of stuff. Sometimes you offload as far as delivery to user space. I'm not going to talk about those here today, but a lot of the principles that apply are really the same. So TCP checksum offload. If you have bought a 100 megabits card, then you'd use this. I'm not aware of 10 megabits cards essentially TCP checksum offload, but somebody probably did it. So all we're going to do is try to avoid looking at every byte in software in the stack. Right? We don't need to look at all that data. We'll just have the hardware do it. So what does this mean? We're going to move calculations from the IP layer and the TCP layer down into the hardware. So we'll sort of shift everything to the left. So we basically have the outline of the stack the same, but we've moved stuff over. Every interface driver declares, is it able to support checksum offload? So what kind of checksum offload does it do? What does it mean to offload checksums? Well, on the generation side, it just means you calculate the checksum and you fill in the right bit of the header. On the receive side, it means you need to validate the checksum, but you don't just want to drop the packet in the hardware, because sometimes you are interested in packets that have invalid checksums. In which case, what you actually need to do is pass a result up. There's this thing called the descriptor ring, which is sort of sits on the interface between hardware and software. The hardware will copy packets into memory pointing to by the descriptor ring, and then the operating system looks along. It has a bunch of headers to keep track of things. And it turns out that this is a good place to pass information to the card and also to receive information from the card that's out of band. One of the things you do when you do this is that you don't want the link layer hardware to have to pass the entire packet to find out where to put the checksum, nor do you want it to have to figure out which bits of the packet to checksum. So we actually pass down hints to tell the hardware where in the packet the checksum should go and which bits we want to cover the checksum. And we even do part of the checksum in software. We usually checksum what's called the pseudo header, so the TCP header with the IP address and the ports. We'll do that in software. And then the hardware will do the rest of that. So these are fairly minor changes to the stack, it turns out. In the input part, we simply look at the packet when we get to the TCP header, and we see if the data from the descriptor was propagated into the mbuf packet header, which is this metadata about the packet in flight. We see what kind of checksum validations happen. Maybe the card supported validating the whole packet, but maybe it just supported validating the data and not the pseudo header. So we may have two parts of it. In a worst case scenario, in fact, the card didn't do anything, and we have to calculate the checksum ourselves. We kind of fall down to the bottom here. So it's actually a really very minor change to the stack. And much the same thing happens in TCP offload. Really, we're just going to shift. But we do all the header building and encapsulation over here, and that all works fine. But we just defer our checksum calculation and let the hardware take care of that. So one of the interesting things is that when you assemble your TCP packets, you actually don't know where they're going to go, what interface they're going to go out. You may have some hints and so on, but potentially it can actually change while you're processing TCP. So the way we structure this in software is that we set flags indicating that we may want hardware offload, but we definitely want a checksum to be calculated. And then eventually you get down to the IP layer, and then we actually calculate it if we discover the interface it's going to go out of after we've made a routing decision. It doesn't support offload. So again, fairly minor changes. At the TCP layer, we don't actually calculate the checksum at all. We just kind of set the flag, we do the pseudo header calculation, and then down at the IP layer, we decide, does the interface we selected actually support it? If not, we'll do all of the deferred checksums in software, which has interesting implications for firewalls, as Julian was pointing out. Okay, so checksum offload is really pretty simple. It's straightforward. It's easy to understand how it might work. But it turns out that although that buys you quite a bit, because you're not cache missing everywhere, you're not doing all these extra instructions, there's actually a lot more that you can push into hardware, or at least into the device driver. So one of the biggest costs in processing TCP is finding out what connection the packet has to be delivered to. You have to go look at all these tables, you have to look at the port numbers and the IP addresses and try and find one of your 50,000 sockets in the system is the right one. So you have hash tables and lists, and you do all this work, right? That is very expensive. If you do that for every packet, you're doing a lot of work. So one of the ideas that's been floating around, and that I think most of the 10 gigabit drivers on FreeBSD now do in software, is that as packets are coming in from the hardware, you look at sequential sequences of packets and you decide if they're from the same connection. And you can do this very cheaply. You just look at the headers and you decide, okay, same IP address, same port numbers. And then the reassembly actually happens in the device driver. So we take these sequential packets and we just sort of stuff them together and do the reassembly, which proves to be really cheap. Which means that when we pass the data up the stack to the next layer, and TCP is looking around for a connection, it does this much, much less frequently. For example, instead of doing 1.5K packets go up the stack, now you're doing 60K packets, but you're doing many, many fewer of them. So this can really improve performance. It isn't just good because you're just doing less looking up. You're also doing a lot less reassembly work in the TCP code itself. So you've really reduced number of instances, number of packets. There's a fixed sort of overhead per packet, so you've really cut that down. And most of the costs in the TCP stack in software don't correspond to the lengths of the packets. There are a few places they do, but most of them don't. So you've really quite improved performance. Let's see what the picture looks like. So basically, either in the device driver or in the link layer driver, we're going to take all these things and we're actually going to stuff them together. And then when we pass them up the stack, we're just doing a whole lot less work. And eventually we deliver them to the socket. We just stuff it in these big chunks, and it goes to the application to pick up. So this is potentially a significant performance improvement. And the reason I kind of draw the iThread line here in the center is that although we currently do this in software, I don't think any of the cards, the drivers right now we support hardware LRO offload. It's easy to imagine that vendors will start doing this in hardware shortly. Understanding is that they will be doing that. So how is this implemented? Well, this is basically just a change to the device driver. As we're looking at our descriptor ring, we know whether there are more packets coming, so we know whether we're sort of at the end of the loop. And for each packet, we show it to LRO and we say, are you interested in this packet? And LRO may choose to eat the packet, append it to the end, and then sort of go on to the next one. And once in a while, LRO says, okay, I'm done. Could you just go ahead and deliver this up to the IP layer now? You have these big chunks. And then at the end, when we run out of packets in the descriptor ring, then obviously we have to flush it up and send it up to the next layer, because we don't want to delay the packet. So we'll at most delay the packet, the length of the number of sequential packets that are actually from the same flow, or to the end of processing of the descriptor ring. TSO is a TCP segmentation offload. It's basically the reverse. Instead of doing the segmentation, breaking it up into pieces in the software layer, as much as possible, we're going to defer that to the hardware. So generate past sort of significant size streams down to the hardware and let it take care of breaking it up into pieces. So how does this work? Well, basically what we've done is we're now passing down very large size chunks, 16K, 64K, potentially more, all the way down through the IP stack. And then when it hits hardware, the hardware looks at the information in the descriptor ring. It sees that we've requested that TSO takes place. One of the things we pass down is the maximum segment size. What size packets do we want it to get broken into when it gets there? And then the hardware spits them out one at a time and generates the checksums and all these other things. So this also significantly improves performance because we have all these per packet costs, queuing and dequeuing on the way down the stack, all kinds of things like that, and we're behaving in a much more efficient way. So potentially this is a significant improvement. So how does this work? At the TCP layer, we detect whether we think the interface is going to go out of towards TSO. We generate these big segments. We just send the whole thing down all at once. We tag each one with how large we want the packets to be at the end. Unlike checksum offload, in checksum offload, we always defer checksums essentially to the IP layer, and then if possible, we send them off to the hardware. In TSO, we actually decide, oh, the router's changed, so TSO is no longer available on the interface. So we actually notify the TCP layer that potentially it has to turn off TSO. So a message size error goes up, and it says, okay, well, I better look up the route and decide what's going to happen now, and potentially turn it off. So what does this look like? Again, the changes are remarkably small. In TCP, at the point where we're calculating segmentation, we basically say if you support TSO, then go with the largest, do as much data as you want to send at once, as much as you can on the window or whatever it is you're using to calculate the amount you're going to send, and otherwise break it up into chunks. So it's actually relatively quite straightforward. So that offloads very simple bits of TCP. Checksum calculation, segmentation, and reassembly. Those are things where the hardware can be very simple to do this. This is very simple computation. TCP offload is actually the full offload of the stack. And I won't talk about it in great detail. But I'll tell you what things do go out. This whole TCP state machine, there's actually per connection state in the hardware, just sort of running in ASIC or something. So all information about connection bindings ends up in the hardware. Some of the data is owned by the hardware, potentially cached and monitored by the operating system. Some data is owned by the operating system and potentially cached by the hardware. So you're pushing information back and forth between the two. Things you offload include all the segmentation and the reassembly, but also the timers and the acknowledgement. Everything moves down there. Basically, you're just passing data and occasional state transitions up and down the stack. And what's kind of neat is the sockets actually directly deliver to the device driver. So they skip the whole IP stack on the way down, which has some interesting implications. And likewise, the device drivers actually, they pass a cookie down into the hardware when the connection is built already. A cookie is attached to it. And in fact, they can bypass the entire lookup of the connection because that cookie can potentially be a kernel pointer to the connection. So you're not actually doing any lookup when you receive the packet. So we've rearranged the lines, right? All the same pieces are still there. It's still doing all this processing. But basically, almost nothing is left running in software, which potentially is a significant win on CPU processing, again, with some side effects. Output is much the same. We do copy things in, we pass it to the socket layer. The socket layer is still doing some buffering. And then we basically hand the whole thing down. Segmentation all the way down to checksum happens in the hardware. So there are some implications. Right? As you begin to offload things to hardware, there are things that are not done in software. So potentially there are bits of software whose behavior is going to change as a side effect of that. Well, one of the most obvious things is that if you have bugs in the hardware, suddenly the layering violation is really obvious, right? Your TCP stack works fine, but your packets still aren't getting there. So that's potentially tricky. It's much harder to deal with fixing bugs in the hardware. You look for new firmware rather from the vendors and so on. But there's some also subtle things. So obviously, everything happening at the socket layer, the application isn't really seeing the difference, right? From its perspective, it's sending and receiving streams, and maybe it's faster, maybe it's not, its behavior is a little different as the data arrive in chunks of this size or that size, right? But fundamentally, it's seeing the same behavior. But there are things that happen below the socket layer, in those bits of the stack that were sort of to run on the other side of the boundaries that happened in parts that are now in hardware. So, for example, packet sniffing is affected by almost every type of offload that it supports. If you run TCP dump on any modern system, the packets you transmit mysteriously appear to have invalid checksums, even though they go out on the wire just fine. Why? Because we don't have the checksums, and TCP dump says, oh, that's interesting, there's no checksum on this packet, but I don't know if you noticed that, but it seems to be invalid. So potentially that's awkward, but it gets even more awkward, right? TCP dump, if you're doing segmentation offload or LRO, potentially seems really large packets, right? What do you think is a person debugging a network connection if all your packets are 60K, right? You know, your Ethernet, you're pretty sure it supports only 1.5K frames. So what is going on here? That's potentially confusing. Not only that, applications that assume that every packet fits into a certain space may find themselves quite confused about the way the system is behaving. Another of these, what Julian mentioned, is that firewalls plug into the stack, right? They plug in below the TCP layer typically. They plug in the IP layer, and they rely on the parse through the packet to make decisions. They're making decisions based on packets that aren't going on the wire. Right? They're seeing the things that are being manipulated by the hardware that may not be the actual packets, that they're doing validation, if they're doing scrubbing, things like that. Potentially they see quite different kinds of things. If you're doing full TCP offload, the firewall will never run, right? Because there is no IP output or IP input going on in software. And many of the cards support some types of firewalls, right? You can push firewall rules into code, but inevitably there's a complete semantic mismatch between what the hardware supports and what the software firewall and the operating system implements. So, you know, do application developers understand that? Do users understand that when they turn on toe, suddenly their firewall gets turned off? You know, they may not, and that really could cause some confusion, especially if you're doing things like traffic rate limiting, right? That often happens in firewalls or in the link layer, and it just won't happen in this case. So, boy, you know, suddenly an application built was limited to 2 megabits a second is using 10 gigabits a second. That could be a surprise. Routing decisions are affected. One of the things that's true about our toe stack is that we are not able to pull connections that have been offloaded back into software again. Right? We basically decide at the time we load a connection, okay, this is an offloaded connection. This means that we cannot move it from one card to another, which means that if the route changes, then we potentially do quite the wrong thing. Right? We send it out of the wrong interface. Now, there are implementations of Toad that do know how to pull things in and out of hardware. In fact, when hardware device vendors build these things, they're actually quite careful to decide, you know, how much is implemented in software, how much is hardware, how do you migrate between them, but we don't currently support that. Another interesting thing is that TCP offload implementations, oh, sorry.
How many concurrent sessions do these cards handle?
I don't know what kind of limits they have. I mean, certainly tens or hundreds of thousands, but it probably depends on the card. Get you an offer offline. So not all toes are created equal. It turns out that implementing TCP in hardware is really complicated, right? Not everyone wants to deal with all the details of it. And so some, and especially due to the number of connection limits, right? Some connections hang around a really long time but do nothing, right? They live in this time wait state. So why leave that in hardware? So toe cards will sometimes implement large parts of the TCP state machine, but then things will get pulled back into software, which means your implementation is much more complicated because for every device you have to decide just how much of TCP offload does it support. So on the Chelsea cards, which we support TCP offload, they actually send and everything forwards happens in hardware until the point where you reach time wait, at which point the Chelsea driver borrows parts of our TCP stack to push it through the remainder of the time wait condition, which is potentially confusing as well. So interestingly, your firewall would affect time wait, but it wouldn't affect the things that lead up to time wait, which is potentially confusing behavior.
Robert?
Yes.
Borrows, you mean that it uses the host version of the TCP stack to push things through the time wait, or?
I'd say there's a spectrum of options there, and the Chelsea driver selects many of them.
Okay.
The answer is complicated. There's a tension between do you want to replicate your TCP stack in the device driver, and do you want to borrow the TCP stack of the host OS, but encode details of the TCP stack, of the host TCP stack in the device driver. Right? And this affects things like binary compatibility with device drivers. If you change the TCP stack, what impact does it have on the device driver? And Chelsea driver actually, some code is copied, but on the whole it tries to use our existing stack costs. So one of the tasks we've been working on as part of getting Toad working is how do you make the device driver more resilient to functional changes in our software TCP implementation. And we've made a lot of progress on that, so it's now, we'll ship Toad in FreeBSD 7.1, but one of the delaying factors there in getting it shipped was how do we figure out how to do this in a way that's more robust and doesn't make it so that as we fix bugs in TCP, we break device drivers, which is obviously undesirable.
Right. The question I was really asking is that migration all the way onto the chip and the hardware, the firmware of the chip as well?
The hardware will have its own implementation of TCP, and basically we set up a socket layer state, and we pass down all the relevant information, and the hardware basically does the rest, right? We'll maintain software-level bindings and so on, so we're aware of all the connections for open, we can do things like say, oh, that's a colliding connection. You can't use that at the same time. But basically, the whole TCP stage engine is in the hardware for what that means, and it is an independent implementation of TCP. It could borrow parts of us for all I know, but from our perspective, it is a black box.
Do the tow engines generally let us do the SINs processing and then take over processing
There is
after?
variation in what the devices do. I believe in the Chelsea cause, the hardware is handling SINs, and we get notifications that new connections are available for accepting. But there is significant variation in what the cards do.
So I was wondering, for example, what happens if you have a card that is negotiating one set of options and then that's,
Right. So
you don't have support?
there is the potential for confusion if parts of the cycle are implemented in software and parts are in hardware and they disagree on what capabilities the TCP are. It will be up to the device driver to make sure that didn't happen. Right now, the only one we support is Chelsea, and Chelsea does all the negotiation itself, the SINs and so on, so it's aware of its own capabilities. And by the time you get to time wait, our stack is as capable as, so we can continue the last few steps, not that it really matters. So let's talk a little bit about software structure optimization. So that's kind of the first sort of 2/3 or half or so was what does the hardware do for you that it didn't do for you before, and how does this affect the structure of software? We made a lot of software changes related to performance, so I'm not going to spend a lot of time on any particular thing, but I want to give you kind of a tour of the things that we've been looking at doing. So the first of these is something called direct dispatch. So when we looked at the picture before, we saw that there were all these stack layers, there were 3 threads involved. So anytime you have multiple threads involved, there are trade-offs. So the cost of switching between threads is non-trivial. The cost of a context switch can be significant, especially if you're running everything on one CPU, so switching back and forth involves exchanging thread states. If they're running on different CPUs, because that's allowed when you have threads, then there's no cost of context switching, but now you're synchronizing between different CPUs. So the more threads you have involved, potentially, the higher the overhead in processing these. On the other hand, the more threads you have involved, the more potential for parallelism there is, because you have different threads that can run independently on different CPUs. So in our implementation, we support an interrupt thread, a NetISR thread, and a user thread, which goes in and out of the kernel, performing actions on behalf of the user process. One of the changes we made is to, by default, actually directly dispatch the full network stack from the interrupt thread and entirely skip the NetISR thread and normal input processing. So why do we do this? Well, we reduce the number of contexts switches significantly, and we guarantee that we're processing all the way through, essentially in the same thread, which usually means on the same CPU. Can bounce around, but on a whole wide thread, kind of stick to the CPU where the interrupts are delivered and we support load downs and things like that. So, so potentially now we're increasing the degree to which we get cache locality when we're processing packets. So this can be a significant performance improvement. Another interesting factor of direct dispatch is that normally when you have multiple threads, you have queues between. So you insert things into the queue on one end, and they come out the queue at the other end, and this queue has a bounded length. So if your system is running at capacity, it's completely saturated, you may have to drop packets. So what are places you can drop packets? Well, you can drop them in the hardware when you discover your hardware descriptor ring is getting too full. You can drop them as an NetISR queue when you discover that the high levels of the stack can't keep up with the device driver. And then potentially if you're doing the UDP or something, you can drop them when you're delivering to the socket buffer, and then they don't get as far as the user thread. When you know that you're going to drop a packet, it is preferable to drop it as early as possible, because that way you're not investing CPU resources in a packet you're just going to drop anyway. So if we move to direct dispatch, we actually don't have one of those queues. We're directly delivering each packet sequentially into the higher levels of the stack. So all of the dropping gets pushed into the hardware. So one potential win when you're running at saturation is you're actually doing less work for packets that you don't care about anyway, which is an interesting side effect. So what does this do to the picture? Well, it doesn't change any of the structure, right? All it does is that it moves the thread boundaries. Now everything runs in the iThread. So we have fewer threads involved in a classic stack, where a single device usually has one iThread. But this turns out to be a really beneficial structure if you have modern hardware which has multiple input queues, because each input queue will get its own iThread. So if your hardware is able to deliver packets in flows to particular queues in hardware, which we'll talk about more in a moment, then each iThread processes independently and potentially in parallel, so you can get significant performance improvements from that as well. Let's talk about another set of optimizations. So the SMPng project was this project, I guess, beginning in FreeBSD 5 to move towards fine-grained locking through the kernel. So FreeBSD 3 first grew SMP support, and essentially all that was there was a giant locker on the kernel. User processors could run on more than one CPU at a time, but whenever they entered the kernel, they were serialized by this giant lock. So the kernel had to live on one CPU at any given moment, which means that you can't take advantage of multiple CPUs to do network processing. And if you remember the graph I had at the front, when I had a series of processes basically just sending bytes, all the work was in the kernel. Almost no work was in the user process for that benchmark. So all the benefits of parallelism were entirely lost to that workload. So in FreeBSD 5 forwards, we moved towards much finer grained locking. We started locking up data structures, we started introducing more threads. We're interested in improving not just the ability to handle parallelism when it exists, but also introduce more opportunities for parallelism. And as you get FreeBSD 6 and 7, this architecture becomes much more mature. We have in FreeBSD 7.0 and 7.1, I think we're very, very pleased with. So one of the things that happens when you're moving towards this fine-grained locking is that you want to start being able to allocate free memory on particular CPUs without interacting with other CPUs. Right? You want to try and allocate memory that's been recently used on the CPU, so the cache lines are in the cache. Even though you don't care what the data is, you don't want to have to move things in and out of the cache and potentially dislodge things. So you kind of want to reuse memory on the same CPU. So a universal memory allocator, UMA, is a slab allocator in the FreeBSD kernel, and it does precisely this. There's a set of central caches, but basically we move the cache memory we're going to allocate it free in particular CPU caches. We work very hard to only allocate it free from those that we can. And now, depending on the workload, like suppose you have a flow between two CPUs, right? You're allocating memory on one, you're freeing it on the other. You want to make it so that at least half the time you're getting this right. You don't want to try and allocate memory that was most recently used on another CPU. You want to try and, in as much as possible, allocate memory most recently used on your own. And you get reasonable flows. You also want to amortize the cost of going back to a central cache, because every time you do that, you have to synchronize, right? Because you're accessing global data structures. So, in as much as possible, you want to entirely avoid synchronization. So we actually use critical exceptions to protect our per CPU caches, because we access them only for one CPU. So another aspect of the SMPng project was allowing the network stack to run on multiple processes at a time. Apply this architecture of fine-grained locking to this very complex piece of software, the network stack. We identified and we locked key data structures. We looked at places that we could add more threads. So for example, in the NetApp example, we now iThreads can run at the same time. They can do processing all the way up the stack in parallel. And on modern hardware, that turns out to be a really big win, since most modern network devices intended for performance that are 1 gigabits or higher will support multiple input queues, so we can essentially process them entirely independently. The SMPng project and the locking down stack are essentially complete. We have no references to the giant lock anywhere in our network stack. But optimization continues, right? Hardware keeps changing. More and more of these cores keep turning up. So how do we try to balance work across the CPUs better? Where do we look for opportunities for parallelism? So we're doing quite a bit of that. One of the changes coming in FreeBSD 8, and actually in FreeBSD 7 is seeing a lot of these, but I'll talk more about FreeBSD 8 in a moment, is a move from mutual exclusion to read-write locking. So the mutex is the sort of most simple primitive for synchronization between CPUs and sort of protects the data structure. So you acquire a mutex and then no one else is allowed to enter code that is protected by the same mutex at the same time as you. Usually you associate these with particular data structures. And this is a good approach for maintaining the invariant that are present in code originally designed for unit processors, right? So not designed to allow concurrent access to the same data structure. However, most of the data structures in the network stack, not some of the really interesting ones like sort of particular pieces of TCP reassembly, but many of the data structures in the network stack, all you want is stability. They hardly ever change, right? So what you want to do is allow complete concurrency but ensure that they remain stable. There are lots of ways to accomplish this, but one of the things we've done a lot of at FreeBSD 7.1 is moving towards using RW locks, which are read and write locks, throughout the network stack. So many of our mutexes have become RW locks. A few of them happened in FreeBSD 7.0, but 7.1 really pushes this all over our TCP implementation and UDP implementation. So one of the side effects of that is that in our UDP code, we now allow fully parallel transmit all the way through the UDP and socket layers, pretty much on the same socket. So there are a couple of workloads that turn out to be really interesting that make use of a single socket to perform I/O to countless endpoints. One example of that is bind the name server, but there are quite a few other examples of UDP applications that just bind one socket. And then they use it for many different threads at once. So UDP itself, the UDP layer, maintains very little state. It maintains maybe address bindings at most. And so really, the potential places where you have to perform synchronization are at the socket layer, where perhaps you have to impose ordering. And then when you start getting down to the IP layer, then potentially you enter routing code and devices that may not support parallel transmit. So what we've done in FreeBSD 7.1 is eliminate mutual exclusion from the UDP layer during most of the interesting paths. So now we're going to run 8 cores at once with separate threads from the user application bind, all transmitting at once. And basically, until you get down to the routing layer and the device driver, you basically run in full parallel, which worked quite well. We've also done a number of other optimizations to UDP, including specialized socket send and receive functions. So it turns out that the requirement for ordering in TCP and other stream-based protocols imposed ordering guarantees on UDP that weren't necessary. So UDP requires that particular streams be kept in order with respect to the sender. But UDP is not interested in all the segments arriving in the same order if they come from separate threads. So the socket code turned out to be acquiring locks to make sure that things happened, that there wasn't interlacing between separate sent packets and so on, things that can't happen in UDP. So we actually eliminated a lot of the locking in the socket layer for UDP, and this significantly improved performance also. Once you've done this, you essentially become limited by routing and hardware queues. And I'll talk more about that. So I said we were moving towards reader-writer locks. So reader-writer locks are interesting, but they still involve atomic operations when you acquire for read. So in FreeBSD 8, we have a new primitive, which is a read-mostly lock, which avoids performing any atomic operations when you just require stability. So when you want to go off and perform a write operation, then APIs get involved, you signal other CPUs to start serializing and so on. But this is quite a useful primitive if you're just looking at address lists, if you're potentially looking at connection binding. So this is not a fully mature technology yet. In particular, it turns out to be not very well optimized for unit processor, so we need to fix that. But on multiprocessor systems, this can lead to a significant performance improvement. And we use this now, for example, for firewall rules and find lists of firewalls that connect. So I mentioned there was this potential issue with hardware concurrency. Right? So it turns out hardware devices themselves are a source of contention. Some hardware devices have non-atomic transactions or operations that you perform on the devices. You send a message to the device and say, kind of set up this thing. You send another message to the device saying, kind of do this other thing, and then you send a message to the device saying, kind of go ahead and do all these other things. And if multiple CPUs are doing all these things at once, they can interlace those, and you can potentially quite confuse your hardware. So the locks that we have in the operating system don't just apply to data in the operating system, they will offer serialized interaction with the hardware. So when you want to start interacting with the hardware that requires atomicity of essentially non-atomic sequences, you acquire a lock, you perform the interaction with the hardware, and then you release the lock, and then another thread can come in and start interacting with the hardware also. And this is a source of significant contention. If you're doing 10 gigabit TCP flows from multiple threads and multiple CPUs on different sockets, they all start slamming into this one transmit queue, effectively, in the hardware. So one of the things that we've been working on is fully parallel transmit down into the hardware. 10 gigabits cards and increasingly 1 gigabit cards will have multiple transmit queues that you can transmit to from independently on different CPUs. So you still have to serialize access to individual queues, and you have to maintain ordering of your flow. But potentially they can all be transmitting at once, and the hardware kind of says, okay, I'll do all assembly down and synchronization and stick it all in the line together. So this can significantly reduce contention as well. So multiple input queues, I mentioned this a little before. This is an example of a situation where when you have a single input queue, you had to have a lock around it, or at least you have to use atomic operations and serialize it in a thread, which we do for some of our device drivers. If you have multiple input queues, you can run multiple threads all independently talking to the hardware, and this in practice improves performance significantly. One of the interesting things is that the hardware has to decide what queue to put the packets in. It wants to maintain the ordering of individual flows. So most hardware will hash the IP header and the TCP header to decide what flow it's potentially in, and then deliver it to a particular queue based on it. Which leads to an interesting problem. It means these connections effectively have affinity for a particular queue, which means they'll tend to be processed on one particular processor. So you need to propagate this concept of affinity up the stack so you can use it elsewhere. And if you have applications that have their own ideas about affinity, then things can be complicated. And multiple queues is basically the opposite, right? This is where we have different queues, and we allow the hardware instead of the software to try and combine them into one stream that's going to go out of the hardware. That's kind of where we are today. We've worked really hard on the parallelism and work, and I think we've really succeeded in improving performance. The performance numbers are very impressive. Some of you may have seen our results for bind and so on. Chris Galloway's in the back of the audience. He's in significant part responsible for the measurements and improvements there. But there's a lot of work left to do. So obviously, I told you about FreeBSD 8, we're looking at read-mostly locks. We're interested in improving our primitives for scheduling, especially as we get larger numbers of cores. The FreeBSD project had its first 230 tool cooler systems donated to it a few months ago. We're working on getting up with working on performance measurements on those systems. We expect it to be really quite interesting. But obviously we need to keep improving these primitives. We have a significant source of contention in our routing code, which is not very parallel, it turns out. Kit Macy has been doing some interesting work on route caches and flow tables, which has shown some significant improvements. I'd like to think that we can get that work potentially into FreeBSD 7.2. We're interested in more TCP input path parallelism. There's some ongoing work. We move towards these RW locks. We're using them extensively in UDP, but we're not using them very heavily in TCP, even on the global data structures most of the time. In FreeBSD 7.2, we'll probably ship read access to those global data structures. On the whole, this doesn't make a huge difference, it turns out, because most processing of an individual TCP connection, once it's going, doesn't require any use of global data structures. But there are some packets that do require global data structures because you may have to change the state of the connection. For example, when you move out of SYN state into the full established state, or you move out of that into time wait, then you're potentially manipulating global data structures, so we end up holding global locks for a significant amount of time. So we like to try and avoid that if we can. Especially as your blend of connections goes from very high performance, small number of connections to lots of connections that come and go quite small, quite frequently. As I mentioned, we're working with local output queue support. This will definitely ship in 8. It may ship in 7. We'll see what happens with that. Also, the software connection affinity is quite interesting. So the hardware is imposing on us this notion of affinity on connections, which we were interested in doing anyway, because we want to kind of get cache behavior working right. And originally, when we started doing the work, we were sure that the software would determine what the affinity of connections was. Well, the hardware is not able to pin individual connections very effectively to individual queues. You really want to pass in a hash that can make the decision very quickly and very easily without pushing off the state back and forth, which really means you need to take the hardware's view of what the connection affinity is, which means the hardware tells you what the affinity is, and then you try and do the right thing up at high levels. Potentially, the hardware and the software may disagree on what they want to do if the application has views on affinity. So how do you get all the stacks to agree on a notion of affinity in an efficient way? It's quite a tricky question. I don't think we really have good answers to that yet. Finally, we're doing work on zero copy. So in FreeBSD 8 right now, we support the zero copy BPF. We allow shared memory segments to be shared between the kernel and user space for purposes of packet sniffing, which has historically been an area where people have done a lot of performance optimization. And so we support that in 8, and hopefully we'll be able to ship that in FreeBSD 7.2. We also have experimental support for zero copy send in sockets already. It's the kernel option in FreeBSD. This requires a little bit more work. On the receive side, it's quite complicated because you want to be worried about kernel memory making it into user space that hasn't been properly scrubbed. You don't want to leak data from the kernel that's not supposed to be there. Also, the way most device drivers lay out packets in memory when they copy it into memory accessible to the processor, they pack it all together, including the packet headers, and applications aren't really all that interested in that. Newer device drivers hopefully soon will start supporting header splitting. We have devices that support them, but the software isn't good. I think that's actually pretty much the end. So, in conclusion, much of this work is motivated by hardware changes, and they're really quite significant. We moved towards a very cache-sensitive and cache-centric design. We have to be able to support parallelism in our software in a way that we never had to do before. Things like hardware offload actually are about parallelism, right? They're about allowing another CPU to do the work for you, but we need to be able to do it all in software as well. And we've seen a very clear progression as FreeBSD versions move forward, starting with 5 really to try and address fine-grained locking. Once we started getting 6, the ideas really became quite mature. And in 7, this is really about very high-performance optimization, starting to address very large core counts, 32 and perhaps potentially more once the hardware starts becoming available. So that's the end. Thank you very much. Happy to take questions.
I don't know whether this is on or not. Yeah. No. Okay. So how does this all get affected by the move to tunneling and virtual networking, and one connection within another connection within another connection?
Right. So Julian's question is, what is the relationship between all this work and a lot of work that's going on in virtualization? Virtualization has become very popular, whether it means VLANs, where you're virtualizing things in the network, or host virtualization, potentially full machine virtualization, and so on. Also, virtualization in the network layer tends to become represented as encapsulated headers as you move up the stack. So to what extent can hardware offload support this? So one of the kinds of offload I didn't talk about was VLAN offload. We support VLAN tag interpretation in hardware and encapsulation in hardware. So a lot of the hardware knows at least a little bit about single layer encapsulation in VLAN. When you get to virtualization of the hardware and the operating system as with virtual machines and so on, things get a little bit more interesting. So one of the things that 10 gigabit card vendors like to do is target improved performance for systems like Xen, because people who buy 10 gigabit cards often buy very expensive hardware and often are interested in virtualization. So the hashes that are used to assign flows to particular queues can be used in other ways than simply ordering based system packets, right? Selecting the same connection between the same queues. Potentially you can do things like select particular MAC addresses and put them in particular queues and assign particular queues to particular pieces of hardware. So the higher end 10 gigabit vendors are looking at how you do that kind of thing. And I guess increasingly the hardware supports that, where you could, for example, even have a Xen machine with a power virtualized driver that actually talks directly to the hardware in a sort of subset way. How do you implement the hardware interfaces so it's safe for a virtual machine to use it? You have I/O and then use and all these other things. So I think this is a very active area of interest. In terms of the virtualization of our own network stack, which is one of our FreeBSD 8 projects, it's not clear to me I mean, it's not immediately clear to me how the two interact beyond what they're already doing. I mean, I guess in as much as you want, in as much as we can take advantage of the support for Zen. So for example, assigning particular IPs to particular queues and trying to get locality that way, I think it does make sense to do things. But the way in which our virtual network stack is designed, I think, is really actually targeted mostly at people who want to have tens of thousands of virtual machines in network stacks. So much higher density than Zen. So we may find that the degree to which parallelism exists in the hardware isn't really intended to scale quite that high. So we'll have to see how it works out. Any other questions?
Yeah, I have a question on the total hardware offload. Is that's running a full TCP stack?
Yeah, pretty much. I mean, time weight isn't in the hardware, right? It comes back into software for time weight.
So there's
yes.
a danger of obsolescence.
Yes, absolutely, right. This is a risk you have when you put things into hardware, that the hardware changes less quickly than the software. Some people might consider that a benefit. But yeah, so one of the points I made was, bugs turn up to existing software in firmware, right? You can go to your operating system vendor and get a patch very easily in case of an open source project or do it yourself. But you have to go to your hardware vendor to get the firmware fix. I suspect, given the price of the devices involved, firmware vendors for the time being will be very responsive to customers who buy 1,000 10 gigabits cards, right? That's a lot of money. But as the technology moves to lower end hardware, and I guess there's an interesting question as to whether they will build. But yeah, I think that's a significant risk. I think the risk of things like IPsec and firewalls is also really significant. Can you align the construction of firewall concepts in the hardware with the ones in the software so that you get consistent semantics? Probably not.
A quick follow-up
Yeah.
before we get to this question. As we get into larger and larger multi-core systems, is it making sense now potentially to dedicate whole cores to particular protocols?
It's an interesting question. Core density is getting pretty high, isn't it?
What was the question?
Sorry, I'll repeat the question. The question was whether, as you move to very high core densities, whether it makes sense to start dedicating particular cores to much more specific tasks, for example, particular layers of the protocol. I think the answer is potentially yes, but I'm not quite sure what direction the topology is going. And there was something quite unexpected happened on the way to current multi-core hardware. When we were really starting on SMPng sort of around 2000 or so, the up-and-coming server lines from Intel were these P4 Xeons, right? And P4 Xeons, for various reasons, were optimized not for locking. Right? Even though there was the hyper-threaded and multi-CPU, atomic operations were incredibly expensive, right? Very, very expensive. We've actually seen locking operations get cheaper relative to regular instructions over time rather than more expensive. I think no one really expected it, right? I was sure, the computer science prediction is that you get more and more parallelism. You want to minimize the amount of communication between them. You get these nice n-squared growth graphs, right, every time you communicate between things. And therefore, synchronization will get more expensive. And the fact that it's gotten cheaper is confusing. It makes sense given what happened with the hardware, but it wasn't the prediction. It will be interesting to see if we return to that direction in which synchronization becomes more expensive again. If you run our, a FreeBSD 7, FreeBSD 8 kernel on quite old hardware, it performs much worse as you add CPUs than it does on new hardware. New hardware, the cost to go to an SMPng kernel is nil, effectively, over a uniprocessor one doing all the atomic watch operations. It doesn't cost any more. So we'll see what happens. The risk is that if you start separating pieces of the protocol processing into different CPUs or different cores, then you start to incur these synchronization costs. So it could be that you start incurring more synchronization costs unless you're very careful or unless hardware supports sort of non-uniform access. So I think we'll have to wait and see a little bit what happens with the hardware direction. But I think it was all worth thinking about because we will have a lot of these cores.
Can I jump on the back of that, which is I saw a talk about from the Barcelona Computer Center recently, or Supercomputer Center, which said that they've done some simulations, and with more and more cores, it's getting to the stage where they can, by taking that picture that Robert showed with all these different threads, actually having more threads and making each thread do just one little piece of the work, they can get better performance. And the reason for that is that the amount of static data that is associated with each flow, or rather with the networking stack in general per section, is increasing. For example, if you take an average stack where it goes through, it comes in and then there's some state defined and then it has to go through a firewall where it has to look up firewall rules and so on. It turns out that by having just one processor doing each bit, they have no synchronization in that spot, and it's always in cache for that spot. And it's becoming that the outside data is getting to be more important than the data in the packet, because in the packet you're just looking at the first 64 bytes of the packet.
So Julian's comment for this is that in some research work, very, very high core density has showed benefits to doing that approach. I think this is arguably not true for the level of density we have now, because we see, in general, a significant performance increase by reducing the number of cores involved. So we literally took the NetISR thread out of the book and saw a massive improvement in performance due to reduced latency. Now, for some workloads, that's not true. One of the workloads that's not true for is packet forwarding, where you have many cores. There's now fewer cores are potentially involved than before if you have a single input to network button. Right now, the density of queues in devices tends to be equal to or greater than the number of cores. But I think we can expect to see that change as core density continues to increase. We may find that devices don't do that, in which case suddenly we'll have many more cores than we have queues. So it looks like perhaps I'm running out of time and should take these things offline. Well, thank you very much.